Okay, so today we're going to be talking about the number 3/4 or 0.75. Unusual, I know, because it's not a whole number like 1, 2, 3, 4, but this one is very important in biology. So Max Kleiber in the 1930s plotted a graph of mass of animal against metabolic rate. Down here we have, you'll have the mouse, he'll have his little legs there, little ears.
Is that a mouse?
That's a mouse.
That's the worst mouse I've ever seen.
Wait till you see my elephant. So somewhere up here, 1,000 times heavier, you'll have an elephant. Let's have a look. Let's try this one.
Well, that's not bad, dude.
That's not bad. It's kind of like a big mouse, to be honest. And then all the way up here, you have your blue whale. Okay, so he plotted the mass against the metabolic rate of all the animals. So mouse, elephant, blue whale, there was also mayflies in there. And as you might expect, with the bigger animals, they need more energy to survive. And that's what metabolic rate essentially measures. How much energy do you need to survive? So smaller animals need a smaller amount of energy, bigger animals need more energy. So one way it could happen is that since the elephant is 1,000 times heavier as the mouse, it would need 1,000 times much more energy. And that, if we had that sort of scaling, it would be linear. And so it would have just a straight line between the metabolic rate and the mass. So the whale, that's 1,000,000 times heavier than the mouse, so it would need 1,000,000 times more energy. Or it could be superlinear. So the elephant is 1,000 times heavier than the mouse, so it needs, say, 1,000,000 times more. It actually needs more than the line originally, the linear line. What Max Kleiber found was that it's neither of those. The curve actually tapers off, and so it's below the straight line. What that means is that the bigger you get, although you need more energy, you can spend it more efficiently. So down here with your mayflies and your spiders and all your insects, they need very little energy, but they don't use it very efficiently. And this scale crosses all sizes of animal, right down to cells, all the way up to the blue whale. It's amazing how this curve describes all the animals. And how does this curve link in with the 3/4? Well, what Max found was that this curve is that the metabolic rate is proportional to the mass to the power 3/4. Now, statistically, it was around 3/4, so something like 0.74 or 0.76. But on average, that's what biologists now take. So this is Kleiber's rule, or the 3/4 rule. Well, when they found 3/4, one thing we want to understand is, where does that number come from? Is it just a coincidence that it's 3/4, or is there some reasoning behind it that we can get at? So originally, when they were looking for this 3/4, they were trying to link metabolic rate and the mass. And so your metabolic rate is how much you use energy. And you use energy, they thought, mostly through heating yourself. And so what affects the heat is, well, your surface area, the bigger your surface area, the more you lose heat. And the bigger you are in terms of your mass, again, the more heat you will have. So they looked at spherical animals. So just for the sake of mathematics, we're going to treat these animals as spheres, because your main body is sort of spherical, and you can at least get an approximation of what you'd expect to get out at the end. We draw our sphere, and we give it a radius r. So that's the body of the animal, okay? So even if you're a mayfly, you'd be a tiny sphere. If you're a blue whale, you'd be an enormous sphere. So the area, the surface area of this sphere, that's proportional to r squared. As you increase r, if you double r, your surface area increases by 4. The volume of the sphere is proportional to r cubed. So if you double the radius, your volume increases by 8. So using this idea that the metabolic rate is proportional to these two guys, you'd expect it to be metabolic rate is proportional to r 2/3. So you'd get a 2/3 power out. So although 2/3 is quite close to 3/4, we wanted to understand where that difference is coming from, because they're close, so it's a good first approximation, but there has to be some reason that we're not getting 3/4. And so what mathematicians have looked at is using the fractal structure inside us to deliver that energy. So the circulation system that we have, the veins, the arteries and the capillaries, is self-similar all the way down. As you zoom into the veins, they look like the whole system. And that's what a fractal is. And using that fractal structure, you can link the mouse to the elephant to the blue whale. And that does spit out the 3/4 power law at the end of it. So as I said, yeah, the bigger the animal, the more efficient you're using your energy. But using this idea of the circulation system being a fractal, you can then start using it to look at cities, because what are cities? Well, they got their own circulation system because they have roads that deliver cars to places, they have water pipes, they have electricity cables, and you can plot those certain things against population, and you get very similar graphs that follow this power rule. It may not be 3/4, but you'll get that it's proportional to the population and it's less than linear. And they're usually following a quarter structure. So whatever this number may be on top, you'll usually find a 4 on the bottom.